Okay, everyone, let's talk about rational functions now. So coming to this section again, we already know about polynomial functions. We did graph quite a few polynomial functions in the previous lecture. So if you need to refresh, please watch previous lecture. I believe it was lecture number 10. So let's begin with our definition of rational function. A rational function, say r of x, is going to be a function that is in the form of r for rational here, and we have in the form of p of x over, let's say, q of x. Now in this form, both p and q of x, these must be polynomial functions. Okay, so if we have something, for example, 2x over square root of x, this is not rational. That's not a rational function. If you have x to 2/3 divided by 2x minus or plus, I don't know, 3, this is not rational either. Okay, so it's very important to recognize what it is that we're working with. We're looking at rational functions whose numerator, denominator are polynomial functions. Now, anytime we work with rational functions, because they are indeed fractions, we got to safeguard against division by 0 because it is undefined. So we technically have to mention that, and therefore from this we can actually come up with a generic domain for all rational function in set Euler notation is all x, so that the denominator is not 0, so that q of x does not equal to 0. That's again the very general domain. So all real numbers except what makes the denominator 0. Now, a rational function is in lowest terms, lowest or simplest form, if if p and q, the numerator denominator, have no common factors. Okay, so that's what lowest term is. Rational function in lowest terms, just like a fraction in lowest terms when there's no common factor in the numerator and denominator. Okay, now the real zeros, this is important, and the real zeros of a rational function, they only come from the numerator. Okay, so the real zeros of r of x, let me just say these come from setting p of x equal to 0. And it's very easy. Let's say I have a fraction, 1 over x plus 1. In order for this to be 0, well, the numerator, notice, is always 1. And there is no way this fraction can be 0, even when x is 0. But suppose I have x over x plus 5 equals 0. Again, the only way this fraction can be 0 is if the numerator is 0, x must be 0, not the denominator. Denominator is 0. In fact, we get into an undefined situation, and we said just now that it cannot be 0. So the numerator must be 0 to find the real zeros. And therefore, the real zeros are the x-intercepts. This is how you get the x-intercepts of the graph. Okay, now let's take a look at an example of rational functions. In our library of functions, indeed, we had one of the functions we had was 1 over x. So notice this is in the form of a polynomial on top, polynomial on the bottom. We have a constant function on top, right, 1, and we have the linear function on the bottom here. The graph of this will look like the following, right? This is from the library of functions. This is what the graph would look like. Okay, now we can actually, and remember here, x cannot be 0. The denominator is never 0. Now from this we can get additional graphs of would be derivatives of these, something like this. And I'm not talking about derivative in a technical calculus term, by the way, here. It would be some form of that hyperbola. This is an oblique hyperbola. The graph is an oblique hyperbola. So it's going to be some form of the graph that I have drawn here. And we can use translations here, right? This is the same as f of x minus h, where you change x to x minus 5. So here we have again a horizontal shift to the right 5 units. So this is 5, and you simply redraw the graph. And that will be the graph of this function. And here's your 5. Okay. And there. So we can use translations still or transformations to graph these functions readily and easily. If I want to do, for instance, let's say I want to graph f of x equal 1 over x plus 2 now. Well, this one would be the graph of 1 over x, only shifted to the left 2 units. The vertical asymptote is at x equal to 2. Previous one was x equal 5. Now for this one, I can redraw the oblique hyperbola that's up here, only adjusted for the transformation for the shift left of 2 units. And there you have this one. So you can now easily we can graph these again by transformations. All right. In all cases here, the range would be the same, but the domain is changing slightly. The domain is what makes the bottom 0. Okay. Now, in the case where we have something like another version of a rational expression, suppose I have 1 over x squared now. Well, the graph of this one again, because the numerator and denominator are polynomial functions, you can plot a few points on this one, and you will see that the graph will look something like this. This portion of it is kind of like 1 over x, okay, but it's much steeper here, and that point is much closer to the origin. Okay, and then this is for when x is positive. The function is indeed even function. For this, f of negative x will be 1 over negative x squared, which is the same as the original, right? So it is an even function. Well, if it's even, that means symmetry with respect to the y-axis. So the other branch of that is going to be the mirror image of what's on the right side. That's for negative x's. And you are looking at a complete graph. This graph will never touch the x-axis because there is no x-intercept. And the reason is because to find the x-intercept of the graph, we're going to set 1 over x squared equals 0. And remember, for a rational function, only the numerator must be set equal to 0, but then numerator says 1 is equal to 0. And of course, that's not true, therefore, no x-intercept. We say we have a horizontal asymptote. We talked about horizontal vertical asymptotes earlier in other earlier lectures. Now we can do, again, use this and transformations to graph other types of 1 over x squared. So for instance, if I have 1 over x minus 3 squared, this would be the transformation of the one that is above, right? Only shifted to the right 3 units. So the vertical asymptote, which is at x equals 0 here, is going to shift to the right at x equals 3. And you simply redraw that function. And there you have it. That will be the redraw of that. And here's my x-axis. All right. Now, what if I have something like, for example, I don't know, 1 over, if I have f of x, let's say 1 over x plus 2 squared. Again, this would be a transformation of the one above, only shifted to the left 2 units, right? So I'm going to go to the left 2 units, the vertical asymptote, x equal negative 2, and redraw. So we don't need to plot points, that's the idea. Plotting points is not the way to do this. Again, if you find yourself setting up x, y like this, negative 2, negative 1, 0, 1, 2, you're missing the point of this, what we're doing here. We want to use transformations in this course as much as possible. And there we have it. Now, I already mentioned about vertical asymptotes. So these lines are vertical asymptotes. Notice the graph does not touch the vertical asymptotes. And the reason it doesn't touch is because if it did touch, then that's the point where we have division by 0. And we know we cannot divide by 0. That's why the graph will never touch the vertical asymptote. All right, so let's define what we mean by vertical asymptote. Now, the word asymptote, the P here is silent. That means you do not pronounce it. Okay, so it's asym. It's as if P is not there, So it's asymptote. Okay. Now, let me write the definition of this, and I'll talk about it. All right, so here I have the definition of a vertical asymptote of the graph of a function. We say that the line x equals c is a vertical asymptote of the graph of r of x, a rational function, if the rational function, notice the function approaches either plus or minus infinity. Yeah, it could go one or the other, or you can just go infinity. It doesn't matter, as long as it approaches one or the other infinities. But the key is that the function, the y value, approaches infinity or negative infinity as x actually approaches a constant, a number c, from either right or left sides. Okay, so if you look at, for instance, the vertical asymptote that's up here, for instance, as I'm going to -2 from the right, the function is rising. As I'm going to -2 from the left, the function is rising. You see that? So that would be the characteristic of an asymptote of the graph of a function here. And that's what we mean by approaching from the right or from the left here. Okay. And let me remove these. Now, so that's the definition of a vertical asymptote. What about a horizontal asymptote? And I can show you those together now. The horizontal asymptote, this time a line y equals c. Notice up here the line was x equals c. That means a vertical line. Y equals c is a horizontal line. That's why we have horizontal and vertical asymptotes. The line y equals c is a horizontal asymptote of the graph of the function of a rational function r of x if the function, rational function, approaches c either this time from above and below. See, for vertical asymptote, we approach c from right and left. This time we approach a line. We approach c, y equals c is a horizontal line, from above and below as x goes to infinity. Previously, the function goes to infinity. So there are marked differences between the two. All right. That means as x gets very large or very small, then the graph has to approach this line y equals c. So here I have now a couple of examples. This one, the one on the right, the smaller one, I'm trying to show what the horizontal asymptote would be. Notice that in this case, as x gets bigger, as x goes to infinity, the function f approaches c, and c is the constant right here. You see that? As x goes to negative infinity, x approaches negative infinity, the function, I'm using r here, sorry, r approaches c. I mean f, r, doesn't matter, it's just a notation. There you go. So from the right, the function approaches c. From the left, the function approaches c. You see that? That's the definition of a horizontal asymptote. Now, this one kind of has both of them, that the one I made up. It has both horizontal and vertical asymptotes. The horizontal asymptote, first of all, is y equals 0, meaning the x-axis. As you can see, as x goes to negative infinity, the function is approaching, right? And as x goes to positive infinity, again, the function is approaching that horizontal asymptote, which is the x-axis. Note also, at 0, the function actually crosses the horizontal asymptote. So for horizontal asymptote has to do, again, for the behavior of the function when x is very large or very small. Now, the vertical asymptote is a different story. Remember, vertical asymptotes can never be touched nor crossed, because at that point, if it did, means we can divide by 0, and we know that's impossible. All right, and I have a note here for you that indeed C1 and C2 are not in the domain, means these are not in. They're C1, C2 are not an element of the domain. They're not in the domain. And that's what you have. As you approach C2 from the left, the function is going to infinity, right? As you go to C2 from the right, the function approaches infinity. So that's the behavior of function. Now, as you go to C1, as we approach C1 from the left again, the function gets very large, goes to infinity. As we approach C1 from the right, the function goes to negative infinity. And those are the characteristics of vertical and horizontal asymptote of a graph of a function. Now, the graph of polynomial functions, again, depending on how much we want to get into this, they could have what we call slant or oblique asymptotes. Okay. So I'm just going to say the graph of R of x may have oblique or slant asymptotes. What do these look like? So for instance, let's say an oblique may look like this. I could have a line that runs like this, and the function must approach it as x gets very small or very large in either of those two fashions. Okay, so for instance, one possibility would be this. Hold on, actually that doesn't look right. Let me modify this to where it's going to work out nicer. I'm going to throw in a vertical asymptote here also, because the graph could have not only slant but a vertical asymptote at the same time. Now the graph has to approach them by definition in one of these two fashions. You see that? So a number of things could happen here. Let's say, for instance, the graph could come like this and approach the slant asymptote in this fashion. And then in here, let's say the other part of this, it could do something like this right there. Okay, you could do that. And that's about it. Now we're not going to work with slants and oblique asymptotes here. I just mentioned that are primarily we will primarily be interested in horizontal vertical asymptotes. Even in your calculus courses, you usually work with horizontal vertical asymptotes. Okay, now the graph of the function may cross its oblique, by the way. It's only the vertical asymptote or asymptote that cannot be crossed. Okay, so how do we find it? How do we find the vertical asymptote? To find the vertical asymptotes of a rational function, you set denominator, set q of x equal to 0. Remember the denominator. And there you have that. All right. Now, let's take a look at a theorem next. This theorem is going to be the theorem on horizontal asymptotes of the graph of r of x of the rational function. So I'm just going to write this theorem and then I'll come and talk about it in just a moment. All right, so here's the theorem on the horizontal asymptote of the graph of a function. Now the theorem goes like this. Let's say we have a rational function. Now the rational function here is again in lowest terms. That means if there were common factors to p and q, numerator, denominator, the polynomial on top and the bottom, then those were removed. All right, so they have no common factors at this point. So I've written the general form of the polynomial on top and then general form of the polynomial on the bottom. Use a for the leading coefficient of the numerator and b's for leading or just coefficients, not necessarily leading. These are all the coefficients for top and the bottom. So we have these two polynomials. Now the degree of the polynomial in the numerator is n. That's the highest degree term on top, coming from the leading term. The degree of the polynomial on the bottom is m. All right. Now, for the part that we are interested in here, if the degree of the numerator, polynomial in numerator, is less than the degree of the polynomial in the denominator, then the x-axis is the horizontal asymptote of the graph. And if the two degrees are equal, then the line equal the ratio of leading coefficients is going to be the horizontal asymptote of the graph. Okay, now this theorem actually has another part which finds these slant asymptotes and other types of asymptotes, but I'm just going to focus on these two portions of the theorem for our work. Okay, now important note here. The polynomial function never has both horizontal and slant. I haven't shown you example of a slant. I've given you a graph of what the slant would look like, right? The slant is again the part that's right there. See that line? That's the slant part. But you haven't actually done a problem with the slant. So in the graph of the polynomial function will never have both horizontal and slant. It's one or the other. Okay. Now the graph of the polynomial function may have both horizontal and vertical. Okay, or it could have slant and vertical like I have here. See, it has a slant and vertical. Up here it has horizontal and vertical. So that could be. And finally the graph may have neither horizontal nor slant. And this is an example of a polynomial function that does not have a horizontal asymptote and it doesn't have a slant. Again, remember the slant, it has to be a line like this. So we don't have that. It looks like I have a parabolic asymptote for this one, right? This parabolic asymptote that you see here. All right. So with that, let's take a look at some examples now, shall we? So let me make up a few of them here. So in example, suppose my polynomial function is given by negative 4x squared. I'm going to divide that by, let's do x minus 2 and then x plus 4. Okay. Now for this one, we're going to determine, let's say, the domain, just the domain of this one, and then we'll graph another one in just a moment. So let's say we want to find the domain. The domain of this rational function is all x's so that x cannot equal to 2 and negative 4, right? Those are the numbers that make each of these factors 0. So we need to exclude them from the domain. Remember, those become the vertical asymptotes. And that's it. That's the domain of this one. Another example. Let's say we want to find the domain of this one. What if the polynomial function this time is x over x cubed minus 64? And again, in this case, x cubed minus 64 cannot be 0. So that means x cubed is 64, and I'm looking for real zeros here. Take the cube root of both sides. Cube root of 64 is 4, because 4 by 4 by 4 is 64. Okay, so domain of this one is going to be everything, anything but a 4. So x such that x cannot be 4. That means you're excluding what it cannot be. So that would imply that everything else is going to work out fine. Okay. Let's look at another example for domain. Suppose this time a polynomial, rational function is made up of these two polynomials. Suppose I have 3x squared plus x on top and x squared plus 9 on the bottom. Okay, now let's take a look. We want to determine the domain again. Okay, domain. So we're going to set x squared plus 9 equal to 0. And then we get x squared is equal negative 9. But then whether x is positive or negative, you square, it will never equal to a negative number, right? This is simply impossible. Again, I'm looking for the real values of the function. So what we're saying is that there's no way the denominator can be 0 by plugging in a real number in for x. Therefore, the domain of this one is all real numbers from negative infinity to infinity. Okay. Now, let's do an example where we have to graph using transformations. Okay, so suppose I want to graph the rational function, which is 1 over x minus 1 quantity squared. Okay, so first of all, domain. Okay, domain is what makes the bottom 0. X equal 1. So domain is all x except 1. X cannot be 1. And indeed, the vertical asymptote is placed where denominator is 0. So x equal 1 is the equation for the vertical asymptote. Now the horizontal asymptote, using the theorem on horizontal asymptotes, look at these two polynomials. They have nothing in common. So the rational function is in reduced or lowest form. And the degree of numerator is 2. Denominator is also 2. If the degrees are equal, the ratio of leading coefficient is going to be the horizontal asymptote. So for this one, therefore, let's see, horizontal asymptote. Oh, actually, I'm sorry. I'm not looking at this one. I'm looking at the one below it. We want to graph this example. This one. Well, degree of numerator, horizontal asymptote. I'm going to say n is, what's the degree of a constant? 0. And the degree of the denominator, m, is 2. 0 is less than 2, so that means x-axis or line y equals 0 is the horizontal asymptote. Okay, so we have that one. And let's check it out. And because it has a horizontal, then it cannot have a slant. So how are we going to graph this one? And remember, earlier we did 1 over x squared, right? We did graph this one earlier. So the graph of 1 over x squared, let me go back up here. There it is. You see that one? We graphed it. So we have some variation of this function, rational function. And therefore, this is going to be 1 over x squared that is shifted to the right 1 unit. And I'm just going to graph it like so without plotting points. Remember, folks, we do not want to plot points here. And there you have that one. Okay. And So we talked about the domain. Now range we usually get from the graph, by the way. The range is going to be from 0 to infinity in this case. And for range, we look at the y values, right? So we're looking at along here. See, there's going to be a graph everywhere except at 0. Y is 0 here. And clearly, let's say we want to find the x-intercept. That's when the numerator equal to 0 for rational functions. But then the numerator is 1, set it equal to 0. That's impossible. So no x-intercept. There are no x-intercept. The graph will approach the horizontal asymptote without crossing it from above. And there is this graph. Okay, now let's take a look at another example. In this next example, suppose I want to graph this rational function r of x is equal to -1 over x squared plus 4x plus 4. Okay. Now this denominator can be written, or I should say rewritten, as a square of a binomial x plus 2 squared. And using the theorem on horizontal asymptote, again, n is the degree of the numerator. A constant has 0 degree because here's why. -1 x to 0 is -1, and there is the degree of that polynomial in the numerator. It's a 0 degree polynomial. The one in the denominator is a 2nd degree polynomial. So that's m2. Therefore, by theorem on horizontal asymptotes, n is less than m. That means x-axis is the horizontal asymptote again of the graph of this function. Right? Now, what about the domain of this rational function? The domain is going to be all x such that x cannot be a number that makes the bottom 0. In this case, -2 makes the denominator 0. All right. And we did the horizontal asymptote. Let's do vertical asymptote. Vertical asymptote, you actually set denominator equal to 0. So we get x equal -2. See, the thing that x cannot be, the very same thing is the vertical asymptote. Now I can graph this one. The x-axis is the horizontal asymptote. And the x-axis may be crossed, by the way. Okay, but the vertical asymptote, which is at -2, isn't allowed to be crossed. This is x equal -2. All right, now let's do our x-intercept, y-intercept. X-intercept, that's when the function is equal to 0, right? The rational function is 0. And for rational function, numerator must be 0. But then again, the numerator is -1, which can never be 0. So there is no x-intercept of this one again. It will not cross the horizontal asymptote. All right. And it is a variation of 1 over x squared, right? And remember, we graph these. They look like so. The negative in front will reflect it. So without the negative, it would have looked like this. Without the negative. But now because we have a negative, it's going to look like so. There you go. It's going to look like that. Now, we need to determine the y-intercept. The y-intercept, that's the easy part, right? You just do r at 0. Plug in 0 for x, so you get -1 over 0 squared plus 4 times 0 plus 4. And that's going to be -1/4. That's what this is. That's a 0 and -1/4. And there you have it. the complete graph of this thing. And once I have the graph, then I can easily do the range. So I usually wait for the range until the end. Otherwise, you have to reason what it is based on this. Okay. So it looks like the range of this one is going to be from -infinity up to 0 on the y-axis, because there is no graph above the x-axis, so y cannot be positive. And because the graph doesn't touch the x-axis, so y equals 0 will never be a value. And there we have that one. Let's do another example. This one, we just want to find the equations of horizontal, vertical, and slant asymptotes, if any. Notice I haven't done any example of a slant asymptote. So this one, let's do one where we find the equation of a slant, but we don't have to graph it. So let me phrase it this way. Suppose we want to find the vertical axis. We want to find horizontal axis or slant asymptote. And the function, we're going to go, let's go x cubed minus 8 and divided by x squared minus 5x plus 6. Now, degree n of the numerator is 3, degree m denominator is 2. Okay, since n is m plus 1, so we have a slant, and that is a condition for a slant. The degree of numerator must be only 1, exactly 1 more than the denominator. Okay, now the vertical asymptote is easy. We can do that in just a moment. But the other thing I have to look for here, by the way, the other thing is this. We need to see if this, sometimes see the rational function may not be in lowest terms. So let's factor this thing and see what happens. If once we factor, there are no common factors, then we're gonna continue on with the original function. All right, now difference of two cubes. This is the factored form of difference of two cubes. This comes from our factoring formula. Let me write that. A cubed minus b cubed. Again, just in time factoring review. A squared plus ab plus b squared. And there we have that. That's how I factor the numerator. The denominator is going to be x minus 2, product of two binomials. And x minus 3. I'm sorry, I said 3, I wrote 6. 2 times 3, that's 6, negative, negative, positive, so I picked up the 6. And then the combination in the OI and FOIL gives me negative 2x, negative 3x, which is negative 5x, so yeah, that'll do it. Okay, now note in here, by the way, see, this is what I mean. We were able to remove the common factor. Now, two things, they're very important, folks. Let's right away go to domain. Okay, and let me reduce this function. So the reduced version of the function, once we remove the common factors, is going to be that, correct? Now notice x minus 2 is gone, right? But before we factor it and remove it, if you look at just down here, if you plug in a 2 in here, 2 squared, negative 5 times 2 is 10 plus 6, you get 0, correct? Division by 0 is undefined, so we cannot have 0. Therefore, in the original expression, x cannot be 2. X cannot be 2, and it cannot be 3. Both of those will give you 0 in the denominator of the original rational function. So, now you may want to say, well, look, in here, isn't this rational function perfectly capable of handling a 2? The answer is yes. If you put a 2 now, we get 2 minus 3 is negative 1, which is in 0, so no problem. Then why are we excluding a 2, right? Well, the reason is because we always look at the original for the domain before we manipulate them. Okay, so it's very important. Now the consequence of the removing common factors is this: removing common factors will cause a hole in the graph of R of x at x equal c, whatever makes that factor that's removed equal to 0. Okay, so I will you just got to be careful with this one. Okay, and we can pursue this further, but just want to point this out. Now let's find the equation. Remember the original intent, we want to find vertical, horizontal, and slant asymptotes. Well, the vertical asymptote is going to be a place where the denominator is 0, so x minus 3 equals 0 and x equals 3. That's the vertical asymptote, the equation for the vertical asymptote. Okay, now because the degree of numerator is greater than the denominator, even in the reduced version, in this one, n is 2, m is 1, n is m plus 1. That means the degree of numerator is one larger than the denominator. Therefore, there is a slant asymptote. If there's a slant, there cannot be a horizontal. So let's find the equation of a slant. So how do we find the equation of slant asymptote? The equation of a slant asymptote in this case is going to be, when we do a long division of x squared plus 2x plus 4 by x minus 3. Now you may have forgotten your long division, but let's review again, just in time review of long division. Suppose I want to divide 17 by 5. Using long division, we set them up like this. Remember, this is the numerator, or it's called the dividend. The denominator is called the divisor in this terminology. So we divide the dividend by the divisor, 17 by 5. The quotient, this is what the quotient is. Oops, sorry. I don't know what happened here. It just went crazy because I got too close to the border. This is the quotient. Okay, so the quotient is 3. 3 times 5, 15. Then you subtract 15 from 17. We get 2. 2 is the remainder. Correct? And 3 is the quotient in this way. All right. So we're going to do the same thing. Now, with algebraic expressions, we're going to divide the first term in the dividend by first term in the divisor. We get x. That's the first term in the quotient. We then multiply quotient by that, just like we multiply 3 times 5. Multiply x times x in the divisor, we get x squared. X times negative 3 makes negative 3x. And then remember, we subtract. We're going to do the exact same thing. We're going to subtract this. To subtract the bottom from the top, we just change the sign inside of this polynomial and add them. These are opposites. 2 and 3 makes positive 5x plus 4 now. And then 5x divided by x, first term. This would be like a new dividend. Divide 5x by x. You get 5 plus 5. Multiply 5 times x minus 3, which is the divisor. We get 5x minus 15. And then we subtract, which means we change the signs and add inside the bottom polynomial. These add to 0, and I have a remainder of 19 now. All right. Now, don't worry about the remainder, but this is the equation of a slant, the quotient. Quotient is the equation of a slant. Therefore, your slant asymptote as equation y equal x plus 5. All right. And there we have them. All right. Now I went ahead and used my graphing utility just to graph this function for you so you see what it would look like having a slant asymptote. Okay, and there you have it. This is the graph. Now it's hard to see, but remember we removed x equal to x minus 2. So at 2 there should be a hole in the graph of this function which you cannot see. And that would be right in here. There should be a hole in the graph of that function. Okay. All right, so we are done with this example now. Now let's take a look at our last example here. So in this example, next example, we would like to, again, find a vertical horizontal asymptote. So we don't need to graph this one. So suppose the expression is x cubed over x to the 4th minus 1. Now, in order to find the vertical asymptote, remember denominator must be 0. So what I need to do is I need to factor the denominator. Difference of two squares, x squared minus 1, x squared plus 1. And in the numerator, we just have x cubed. I'm using this special factoring formula for difference of two squares. Okay. And the squares, by the way, x to the 4th minus 1, that's like x squared squared minus 1 squared. So here's your a and there's your b in the general form. Okay. Now x squared minus 1 in the denominator, that itself could be written again using difference of two squares as x plus 1, x minus 1, and then x squared plus 1. So that's a complete factored form. Now degree of the numerator, no common factors, we cannot cross anything out, so that is in lowest form. N is 3, degree of the denominator, let me write it here. N is 3, m is 4, n is less than m, therefore, again, the x-axis is the horizontal asymptote. Therefore, the horizontal asymptote has equation y equals 0. That's the equation for the x-axis. Okay, because 3 is less than 4. By theorem on horizontal asymptotes. Now, for the vertical asymptotes, we set the denominator factors in the denominator equal to 0. And let's see what's going to happen here. So from the first factor, we get x equals -1. There is one vertical asymptote. Next one, add 1 to both sides, x is 1. So we got two vertical asymptotes on this one. Subtract 1 from both sides, and again, no square is going to equal to a negative number. This is not real. Impossible to square real numbers become negative. So there's no horizontal asymptote coming from that factor. In fact, the domain of this function is going to be all x except -1 and 1. Okay. Nothing makes x squared plus 1 0, so that one is good. And therefore, these are the equations for the vertical asymptotes. So we got our horizontal asymptote and we got our vertical asymptotes. We are good. And that's all we wanted to do in this section, everyone. Hopefully everything makes sense to you. Please, again, if you have to, go back and review some of the things that may be a little bit more challenging to you here. All right, so with that note, again, thank you for watching, and see you in another video. Bye.